1.2. The Complex Triangle Inequality. In the previous video, we showed that there are a lot of similarities between C and R2. Both contain numbers that are ordered pairs and they live in some 2D plane. Addition in C and R2 is exactly the same, and the idea of magnitude in both of these systems is also equivalently defined. We'll also find that distance, the measure of how far one number is from another, is also similarly defined in C and R2. Suppose I have two complex numbers in C, z and w. Remember, if I add z and w together, it's exactly the same as adding two vectors in R2. Simply use the parallelogram rule and add head to tail. The complex triangle inequality states that the distance from the origin to the point z plus w is always smaller than or equal to the distance going from the origin to the point z, then going from the point z to the point z plus w. Another way to phrase this is that the magnitude of the z plus w vector is always less than or equal to the magnitude of a z vector plus the magnitude of the w vector. Simply put, this is another way of saying that the shortest distance between the origin and a point in the complex plane is to go in a straight line, rather than take some non-straight angled path. Obviously, this is true. We know it just by experience. But can we prove that this inequality indeed holds in the complex plane? Before we prove the complex triangle inequality, we need to prove a lemma, which I'll call the basis magnitude lemma. The lemma states that the real part and the imaginary part of a complex number are always less than or equal to the magnitude of that number, and greater than or equal to the negative of that magnitude of the number. If you are unfamiliar with these curly letters re and im, remember that a complex number z has a real coordinate, a, and a complex coordinate, b. Thus, the real and imaginary parts of z are just a and b respectively. We will prove this lemma, but before we do, take a second to confirm this in your mind and make sure it makes intuitive sense. Here's the proof. Suppose we have some complex number z. Then, as we defined in last video, the magnitude of z is just a and b added in quadrature. However, given that a squared and b squared will both always be positive, then the square root of a squared plus b squared will be bigger than or equal to just the square root of a squared. Simplifying, we see that the magnitude of z will always be bigger than or equal to a. But a is just another notation for the real part of z, re, z. So the magnitude of z will always be bigger than or equal to its real part. Therefore, doing some algebra, we can see that proposition 1 in our lemma is indeed true. I won't show proposition 2 of our lemma because the proof is exactly the same. You can do that on your own. Now that we have the lemma, we can get on to proving the complex triangle inequality theorem. Here's the proof. Suppose we have z and w in the complex plane. Then the real part of z times the conjugate of w is less than or equal to the magnitude of z times the conjugate of w. We just showed this from our lemma. In an earlier video, we showed that the magnitude of z times the conjugate of w is just equal to the magnitude of z times the magnitude of w. Now, again, in another video, we showed that the square of the magnitude of the sum of two complex numbers, say z and w, is equal to the square of the magnitude of z plus the square of the magnitude of w plus 2 times the real part of z times the conjugate of w. If we take line 3 and substitute in line 4, then we get some equation like this. We can factor this left side into something more compact, namely the square of the magnitude of z plus the magnitude of w. And if we take the root of both sides, voila! We get what we set out to show, the complex triangle inequality theorem. That's all for now. Thanks for watching.